Hey guys, Buildzoid here, and today we're going to be doing another X670 motherboard PCB breakdown. This time it's the Gigabyte X670 Aorus Elite AX. The board was provided to me by Gigabyte, so big thank you to them for sending the board over. And with that out of the way, let's get right into it. So at the time of shooting this video, the board tends to go for around $290 US, which makes it one of the cheaper X670 motherboards out there, but obviously not the cheapest. I think the cheapest ones I've seen are like $250-ish. Anyway, going from a like the difference between an X670E and an X670 motherboard is that the X670 boards are cheaper, and the trade-off is that you get less PCIe Gen 5 connectors. It's not that you don't even get any of them, because you do still get this M.2 slot as Gen 5, and the reason that you get this one M.2 slot in PCIe Gen 5 is because it's, well, right next to the CPU socket, so the PCIe Gen 5 signals don't have to travel a significant amount of distance, and also M.2 slots are only like 4 PCIe lanes, so it's not as much of a problem to, connect this to the socket with like Gen 5 levels of reliability compared to connecting this thing, which has significantly more signal links in it, or all of the M.2 slots down here, which are further away. Anyway, so what that does mean is that, yeah, you get this one Gen 5 M.2 slot, and then everything else on the board is PCIe 4 or slower. So this is a PCIe 4x16 PCIe slot. These M.2 slots are all PCIe Gen 4. One of them is from the CPU, the other two are from the chipsets. Yeah, the other two are from the chipsets. Not sure which chipset right now. You can check the motherboard manual for more details. This by 4 PCIe slot is Gen 4, and then we have a by 2 PCIe slot down here, which is Gen 3. I am really not sure what you would do with a by 2 PCIe slot these days, because even, like, a lot of capture cards are by 4. And so, yeah, I am not, like, if this was a motherboard that didn't come with Wi-Fi, I'd tell you, oh yeah, you could stick, like, a Wi-Fi card into there, or maybe a networking card, but if we look at the rear I/O, that doesn't really make any sense to do because it comes with Wi-Fi 6E. You get 2.5 gig Realtek LAN built in, so I'm not sure that you can put a 10 gigabit card on a X2 PCIe slot. If you can, then I guess you could do that, but I'm pretty sure 10 gig LAN is like PCIe 4. And if it is, then yeah, you're not putting it in that by 2 3.0 slot at the bottom of the board. Anyway, but back to the rear I/O, you do get a ton of USB Type-A ports. There's 12 of them, which, yeah, like, honestly, this is really surprising for a motherboard in this price range because it's not typical to see a rear I/O this filled out on a motherboard that's under $300. So, yeah, that's kind of surprising. You do get an HDMI port because Ryzen does have a built-in iGPU now. And you do get a single Type-C port, which is potentially a downside if you want more Type-C ports. There are motherboards that offer more Type-C ports than this on the rear I/O. So, yeah, that's kind of one of the other sacrifices that you sort of get with this board, because, fun fact, Type-C ports do add manufacturing cost compared to Type-A ports. Like, Type-A ports are just cheaper. It's not a huge difference, but, if you keep adding on, like, PCIe Gen 5 adds a bit of cost. Type-C ports add a bit of cost. And if you keep doing that long enough, you end up with a $500 motherboard. So, yeah, that's why this is... Like, you do still get an awful lot of connectivity. It's just not the expensive version of any of those connectors, basically. You do also get a Q Flash Plus button, so you can actually update the BIOS of the motherboard without even having a CPU installed, and this can potentially recover from BIOS corruption. That's not its intended purpose, but it can sometimes work for that. So that's pretty cool. Anyway, let's go back to the internal functionality of the board, or test bench functionality of the board, because this board has a surprising number of buttons for a $290 board that's, like, not really meant for, like, overclockers. You get a power button, you get a rebindable reset switch, and I was really excited about this, but unfortunately, similar to, like, this is a really great feature on Gigabyte's Z690 boards, and I imagine they're going to have it all over their Z790 boards as well, and it's going to be amazing there as well. Here, it unfortunately really does only, well, actually, it has some other functions, but that I've not tested, but the most important, like the best function that this reset switch offers on a Z690 board is safe boot. Unfortunately, on AMD platforms, third-party safe boot implementations do not work very well, or ever at all, as far as I know. Gigabyte tried to have the same functionality on their X570 boards. It doesn't work on those either. On their Z690 boards, you can reconfigure this button to act as a safe boot button, and then it's amazing, because if you screw up your BIOS settings, you don't need to clear CMOS, you don't lose any of your progress, you just hit the safe boot button and you're back in the BIOS with all your terrible settings, and you can go fix them. But yeah, on this board, that does not work, and as far as I know, the reason is that AMD has like a built-in failed overclock recovery system in the AGSA that doesn't work either, and because that system exists, like third-party safe boot implementations don't work. As far as I know, this isn't like, so as far as I know, this isn't a Gigabyte problem, this is very much an AMD motherboard problem, and it sucks, because on Intel motherboards, this button is amazing. It's my favorite, like, feature that you can get. Like, one of my favorite features to have on a motherboard is a safe boot button. And unfortunately, on AMD motherboards, this button just can't do that. So that really sucks. But maybe sometime in the future it might get fixed. I kind of doubt it, but, you know, we can hope. And if it does get fixed, then yeah, this would be... Honestly, this would be one of those features where it's like, if this ever worked, it would be a very good reason to get this board instead of another board, depending on how much memory overclocking you plan to do. Anyway, let's keep going down. You get some troubleshooting LEDs over here. No postcode, unfortunately, so you just get the basic indication of, like, GPU not initialized, like, GPU initialization, CPU initialization, memory initialization, boot device initialization. Depending on the platform, this can be enough, but I do prefer having a postcode to, you know, get more details in terms of boot up errors. So, yeah. Below that, we have an internal Type-C header, and, okay, well, this is another one of the downsides of this board. Actually, this seems to be a pretty common downside with a lot of AM5 motherboards. There's just not many Sata ports on them. So you do only get 4 of them on this one. Yeah, so if you're, you know, if you prefer SATA drives to M.2s, or if you just have a lot of SATA drives that you want to plug in, yeah, this board's not going to take more than 4 of them. I guess you could get like a PCIe to SATA card for your 3.0 X2 slot at the bottom, and that could kind of work for that. So I guess that's a use for this, because I really wasn't sure what else you'd do with it. Anyway, we do also get a clear CMOS switch, which, clear CMOS button, it's not really a switch, but it's labeled switch. I mean, to be fair, the reset button is also labeled switch, so whatever. The thing is, I've never really, like, this isn't really a test bench board, and if you have the board inside a case, an internal clear CMOS button is not really that useful because you need to take the side panel off. However, what you could do instead is you could just wire up the clear CMOS jumper to your, like, front panel reset button, and then you get an external clear CMOS button, which is pretty neat. And it's also worth noting that on Gigabyte motherboards, there is a last known good function built into the BIOS, and the way that works is as long as you've booted the motherboard all the way into Windows, or at least to the, like, Windows login screen, the board will remember your last set of settings. So if you hit that clear CMOS button, you're set, like, you can still recover your overclock settings. It's not super reliable. Okay, like, there have been situations where I've been burned by over-relying on Gigabyte's last known good function, especially on AMD motherboards, because on AMD motherboards we don't have a proper safe boot, but it is really convenient when you don't, like, lean on it too much and then end up losing all of your progress, because, yeah, it's not like, the conditions in which it works are very specific, and if you don't, you know, if you don't rely, like, if you don't consistently go all the way into Windows, or I think if you fully power cycle the board, as in you, like, cut 5-volt standby power, last known good doesn't work anymore, I think. So, yeah, like, I wish we had safe boot instead, instead of having to rely on clear CMOS. But as far as I know, like AMD boards and safe boot are just not a thing. So that really sucks. Anyway, let's move on to the power delivery. The board does come with two 8-pin power connectors, but unless AMD is planning to release a 300-watt CPU, well, unless you manage to buy a 300-watt CPU for this socket, you do only need just one of them, right? A single 8-pin power connector can easily provide 300 watts of power, and if you have better cabling from your power supply, like if you have 16-gauge cables, you can potentially push over 400 watts of power through one of these connectors, or even more than that, if, you know, everything is perfect. So, yeah, there's really, like, if you have a power, like, and the thing is, the 7950X is not going to pull 300 watts of power unless you do something exotic for your cooling solution. So basically, even if you buy a 7950X, your power supply only needs a single 8-pin. You really don't need the second 8-pin. You can just kind of pretend this doesn't exist, because as of right now, there is no CPU that you can put into this socket that would justify plugging in both connectors. So yeah, if you're worried about this, well, just don't be worried about this, because it doesn't do anything. Literally doesn't do anything. Anyway, let's talk about the actual VRM itself. So it's all of this. Oh, I guess I could have highlighted both control. Too late. Anyway, so this over here is, of course, the SoC VRM. Then this down here is the VDD Misc. I guess I could also just shorten that down to V miscellaneous. And this is a stupid name for a voltage rail. Like, there are actually worse voltage names, like worse names I've seen, but miscellaneous power rail is just, I don't like it. And this is the official term. It literally, in the BIOSes, it's just VDD Misc. It primarily powers the Infinity Fabric links. So yeah, I don't know, they could have called it something else. The thing is, like, that voltage is used for a bunch of other stuff on the SoC, and so it's labeled miscellaneous, even though in terms of its overclocking applications, it's primarily the Infinity Fabric. Anyway, and the rest of this is a vCore, is just vCore. So vCore and vSoC are controlled by this chip over here, which actually I'm just going to label it inside. So this is that is a horrible X. This is an XDPE 192C3B. This is, as far as I know, a 12-phase controller. Here it's running in 8+2 phase mode. The 8 phases go to the vCore, the +2 goes to the SoC, and at this point you might be looking at this and going like, but there's a lot more than 8 power stages here. Is there any doublers? And the answer to the doublers question is no, there is no doublers, because doublers aren't cool anymore. And to be fair, doublers really, like, don't make a ton of sense. Or at least they don't make a ton of sense once you've hit like a 8-phase VRM. They kind of make sense if you had like a 3-phase or something and you're doubling up to a 6. But yeah, when you're starting with an 8-phase controller, like your phase interleaving is already so high that you've hit like major diminishing returns going above 8 phases worth of interleaving. Anyway, so what's going on here in terms of the actual phases is that each phase is made up of 2 power stages and 2 inductors, which are not, well, they're run in parallel. Basically, the 2 power stages gets fed the same PWM signal from the controller, so they both turn on and off at the same time, which means that your inductors effectively end up being connected to the, because you have plus 12 volts over here. So when the high side MOSFET in both of these power stages turns on, it connects both of the inductors to, both of the inductors get connected to the 12-volt power plane at the same time through those high side MOSFETs. And that's the reason why this board uses somewhat high inductance by gigabyte motherboard standards. Like, these inductors are 400 nanohenries, which is the highest inductance I've seen in a vCore VRM from Gigabyte in a while. Because Gigabyte already has been doing this on some of their like B550 boards, and I think even some of their X570 boards, that they'd be putting power stages and inductors in parallel like this. But there it's typically been with 300 nanohenry inductors, not 400s. Now the funny thing is this has like some benefit, so this has benefits in reducing the amount of ripple on the 12 volt side of the VRM. Potentially it harms the voltage regulation on the output, as you do have more energy stored in the inductors, and so on a load release you have the potential for more overshoot. Though depending on the overall design of the VRM and tuning of the control loop, that can also be minimized. So yeah, it's just kind of like this isn't really a assessment, like this isn't a good or bad judgment of the choice of inductor that Gigabyte has made here. It's just kind of interesting to me that this board uses 400 nanohenries because I was expecting 300. So yeah. Anyway, let's talk about the actual power stages. And for vCore, Gigabyte is using the TDA 21472s, and since there's 2 of them in each phase, there's 16 of these in total. And these are 70 amp smart power stages from Infineon, and at this point you might have realized that this is actually like more vCore power stages than what Gigabyte had on the X570 Aorus Extreme. And that's correct. Like, this is just straight up in terms of current handling capacity. This is just more powerful than the VRM that Gigabyte had on the X570 Aorus Extreme. Which is also why I made a video of running this board with no VRM heatsink installed in Prime 95, because this is massive overkill. Especially when it's combined with the 8-layer PCB, because that also means you can have a very substantial power plane, and the PCB just has more copper in it, so it can dissipate more heat more effectively, as well as just produce less heat, right? Because larger power planes means you have lower resistance between the VRM and the CPU socket. So yeah, in terms of current handling capability, this VRM is absolutely ridiculous. And in terms of theoretical efficiency, at 1.2 volts output voltage and 400 kilohertz switching frequency, this VRM should be able to output, how am I so bad at this? Kilohertz. Anyway, so yeah, 1.2 volts output voltage, 400 kilohertz switching frequency. Only the heat output of the power stages, so we're not accounting for power losses in the inductors or power losses in the power plane, just the heat output of the power stages for 200 amps should be about 16 watts of heat in total, which means that's 1 watt of heat per power stage. And that's the whole reason that I decided to do the video. Well, the fact that this VRM was already on a board that I ran without VRM heatsinks without any issue. Well, basically, a very similar VRM was on a board that I ran without heatsinks without any issues, and the fact that on paper this really doesn't produce any heat is the reason that I made the video of running this board in Prime 95 with no VRM heatsinks. But, you know, if you do keep the VRM heatsinks on the board, they are actually very, they're good heatsinks. So, you know, Gigabyte is sinking heat directly from the power stages with some very soft thermal pads, and then we also have some thermal pads on the inductors themselves just to suck even more heat out of the board, because actually pulling heat through the, casing material of a power stage is generally not that efficient. So, yeah, a lot of the heat transfer actually happens from, the surrounding power plane rather than directly through the power stage itself. And that's also why, sinking the inductors can help, and also by sinking the inductors, you can pull some of the heat out of the, vCore power plane itself. Not that, you know, with an 8-layer PCB that's particularly necessary, but it does help. Anyway, so that's how the heatsink is connected to the VRM. And then for the actual design of the heatsink, we've got a passive heatsink design that makes, you know, sense for passive operation. So large gaps between the fins. The fins are relatively thick. And yeah, this isn't the highest surface area VRM heatsink that you can get on an X670 motherboard, but the problem with a lot of the super dense VRM fin stacks is that they actually trap hot air. If you don't force air into them, the air will kind of get stuck in them because convection is very, very weak. And the hot air basically needs to have room to pull fresh air in as it rises out of the fin stack. So if the fin stack is too dense, you have like terrible, like the passive cooling capabilities of the heatsink are actually awful, which is why like, you know, there are passive heat sinks designed for cooling CPUs, and if you've ever seen any of those, they don't use super dense fin stacks because super dense fin stacks basically end up acting. You can kind of think of it like a sponge has a ton of surface area, but getting air through a sponge is very difficult because it's too dense. So a similar thing applies to VRM heatsink designs. Now, the boards that use the super high surface area heatsink designs have even more overkill VRMs than this does, so there it's even less relevant what kind of heatsinks they have, but yeah, this is a totally sensible heatsink design, and also the board doesn't need it in the first place, which is just like an added bonus. So even if the VRM heatsink design was bad, it doesn't matter, the board literally doesn't need a heatsink. As demonstrated by me running it without a heatsink in Prime 95. And the hottest part of the VRM ended up at like 75 degrees Celsius, and that's this area right here, or I think it was 77 or something. And the temperature sensor for the VRM is, I believe, this right here. There's just a little, like, NTC, I think it's an NTC resistor, and that acts as the temperature sensor for the VRM. So, yeah, in terms of current handling capability, this VRM is massive overkill. And this is a $290 board. So, yeah. Anyway, if you decided to do LN2 overclocking with this motherboard, you still wouldn't really need a VRM. Actually, you wouldn't need a VRM heatsink because even at 300 amps of output current, the VRM would only produce about 23 watts of heat. And generally speaking, when you're doing LN2 overclocking, you don't run Prime 95 for an hour. Okay, that's just not a thing that people do. Usually you'll be running benchmarks like Cinebench, and, you know, with a 7950X, Cinebench is not a very long benchmark. So the VRM will probably actually end up freezing over if you don't use some kind of PCB heating system to prevent the like LN2 pot from sucking all of the heat out of the board itself. So, yeah. Anyway, 400 amps output, the VRM would produce about 32 watts of heat. And so now the VRM heatsink would definitely be very useful. There's also no way we're going to have a 400 amp CPU on this socket, so I don't really see how this is a practical like, this isn't a practical concern, but hey, maybe AMD will somehow squeeze a Threadripper into one of these. No, like, I'm being sarcastic. Anyway, 500 amps output, the VRM would produce about 44 watts of heat. Actually, speaking of Threadripper, this isn't really that different from the VRMs you find on some Threadripper motherboards either. So, yeah, that's why it's so incredibly freaking overkill. Anyway, moving on to a part of the voltage regulator that is sensible, we have the SoC VRM. Relatively sensible. Sensible in comparison to the vCore. Because for the SoC VRM, Gigabyte decided not to use the TDA21472s. They are quite expensive, and instead they went with NCP 303160s. And if I'm not mistaken, Gigabyte's using these 60 amp smart power stages on some of their other motherboards in their AM5 lineup, which would explain why we see them here used for the SoC VRM, because you wouldn't really want to be buying one power stage for one specific board. That doesn't really make a lot of sense if you're making a lot of boards. But yeah, these are still 60 amp smart power stages. They're not as good as the 70 amp smart power stages used for the vCore, but the SoC power rail needs to provide very little current to the CPU, so yeah, this is still extremely overkill. In fact, as far as I know, there are some boards that have a single-phase SoC VRM, so yeah. This is like, yeah, this is just a very, very overkill SoC VRM. I guess once we see CPUs with a significantly more, actually, once we see APUs with like a substantial iGPU, this might actually be useful. But as of right now, it's just, yeah, like, this is just another contributor to the fact that you can run the board without the VRM heatsink installed. Here we see 150 nanohenry inductors, which isn't really that surprising because that is what Gigabyte has used on their other Infineon-based, like one power stage per phase VRMs, right? Like this is the SoC VRM here is a two-phase, so each power stage gets its own separate PWM signal from the controller. Unlike the vCore VRM. So the vCore VRM has these higher inductance inductors because those inductors end up connected to the 12-volt power plane at the same time, very regular, like every time the power stages get sent to high pulse, right? But yeah, here that's not the case, and so we have 150 nanohenries per phase. So yeah, that's just kind of interesting design choices. I'm not really sure how it affects. Like, the funny thing is, I have actually measured the voltage regulation of the SoC rail on some AM4 motherboards, and it was a straight line. I didn't make a video about it because there wasn't really anything to look at. It was just like, oh, this is the SoC voltage. It's a straight line. Which is kind of neat, but also very boring to look at. Like, it's a straight line going from idle to, like, running LinPack. So, yeah, it's just... And then, as far as I know, with the 7000 series, the SoC pulls even less current than it used to. So, yeah, until we see iGPUs, this basically doesn't have to do any work, or more substantial iGPUs. It doesn't have to do any work. Anyway, let's take a look at the Misc voltage regulator, and for that we've got a Renesas RAA 229621. This is the exact same controller that you would find even on an X670 E Aorus Extreme, because Gigabyte is just copy-pasting this two-phase VRM around their boards. So yeah, the power stages used here are a pair of ISL 99390s, and these are 90 amp smart power stages from Intersil, or Renesas, because Intersil is now owned by Renesas. So we've got more massive overkill over here, and I think these are 300 nanohenry inductors. They could be 400s. I'm not really sure. It doesn't really matter. I don't think I managed to read them. I think the label on these is like inside. So yeah. But anyway, yeah, 90 amp smart power stages for powering, I think just primarily powering the Infinity Fabric. Massive overkill. As far as I know, there are boards with this also being a single phase. So, yeah. Anyway, I guess let's talk about the capacitors next. So, for output filtering, like bulk output filtering for the vCore VRM, we've got all of these APAC, which is a Taiwanese capacitor manufacturer, very popular with Asus and Gigabyte on their like low-end to mid-range motherboards. 5,000 hours rated at 105 degrees Celsius. And they're 560 microfarad aluminum, like through-hole aluminum polymers. And they're rated for 6.3 volts. And this is pretty typical for a, as far as bulk capacitors go, this is pretty typical for a motherboard like this. Since these are aluminum polymers, like even if you do run them at that rated temperature, like they don't die at the end of that lifespan. They basically will lose. Well, actually, the funny thing with aluminum polymers is that they won't necessarily lose their capacitance, but they will potentially have like 20% higher ESR than they did when they were new. So yeah, like polymer capacitors are like they just don't have the concerns that your liquid electrolyte capacitors had, and those haven't been used on motherboards for like 15 years at least. So yeah. Anyway, so these are not as high rated as what you would find on some of the higher end boards. Like higher end boards will often use 10,000 hour rated capacitors, but really this doesn't make a difference in my experience. You'll see more of a difference, like, well, I'm not sure how it would affect the voltage regulation if you measured it after the motherboard's been run hard for like 5 years or something. So if you had the board as like a rendering workstation, the lifespan might... Well, actually, no, because the VRM on this board runs ice cold. So, yeah, no, it doesn't matter, right? Because that's 5,000 hours at 105 degrees. But this VRM maxes out at like 75 degrees right here. So, yeah, no, and that's without the VRM heatsink. With the VRM heatsink, it's going to be running even colder. So, yeah, no, I don't like... Out of the box, I've not seen a performance difference based on capacitor like through-hole capacitor selection and like what brand they are. That's just not a thing because yeah, higher end boards will regularly use like Nichicon capacitors, but like measuring the voltage regulation on, you know, brand new condition boards, APAC capacitors, Nichicon capacitors, they basically perform the same. Actually, well, more like the performance depends on other parts of the VRM design more than it does on who made the capacitors, especially when they're well, the type of capacitor used can affect it quite significantly, but these are all through-hole polymers that we're talking about here. So, yeah, nothing to complain about with the output filtering. For the input filtering, we've got a relatively substantial input filter, as there's 6 270 microfarad APAC capacitors, and those are rated for 16 volts because they're sitting on the 12 volt rail. It's also worth noting that the endurance of the capacitors gets a bit better if they're like rated for a higher voltage than what they're being used for. And V-core on, you know, X670 motherboards is like 1.5 to 1. It maxes out at like 1.5 volts in regular operations. So yeah, these are massive, like these are not going to have any issues. That's just not a concern. And the reason why 6.3 volts is used is because 6.3 volt capacitors are just used all over the board, right? Like these are the exact same capacitors that you see in the output filtering of the V-core VRM. Same, well, actually we don't, oh, interesting. I was expecting to see a big fat 16 volt and 6.3 volt right next to the PCIe slot, but yeah, I guess not necessary. Or mostly optional, and so they've decided, yeah, I guess making space for the M.2 SSDs. They do still have the multi-layer ceramics. Anyway, now the SoC VRM gets a bit more, like a somewhat more fancy output filter, as it uses 330 microfarad SMD aluminum polymers. And the reason why I consider these a bit more fancy is because, well, they're literally more expensive than your through-hole capacitors, but also these have lower ESR, well, not lower ESR. ESR you can actually get basically the same in both SMD polymer and through-hole polymer, but these have an ESL advantage inherent to their physical just shape. So yeah, and ESL is the equivalent series inductance. Not that I think the SoC rail really needs better filtering than V-core, but this is mainly done for space concerns, right? Like there's just not that much room for capacitors in this area of the board, with the way the power plane is laid out and that kind of thing. So, yeah. And I guess if you did have an iGPU, this might actually be beneficial to the voltage regulation for that. Well, a substantial iGPU. I mean, yes, technically 7000 series CPUs have an iGPU now. It's like 2 compute units. It doesn't pull any current. So, and you can't overclock it. So, really not a concern. Anyway, so that's the input filtering and output filtering of the board, and it's pretty standard for, you know, a board in this price range. In terms of performance, you'd actually have to measure it with an oscilloscope. Unfortunately, when it comes to voltage regulation, it's not just the parts that are used. It also heavily depends on the tuning of the voltage controller itself. And so the parts here don't inherit, so the parts do affect the performance, but like there's a whole separate, you know, like I guess the best way to put it is like you could have great VR, like you could have a great, really well tuned control loop on the controller and then terrible parts, and the overall performance will be kind of miserable. Or you can have great parts and terrible tuning of the controller, and the overall performance ends up being miserable. So, yeah, but from in terms of physical aspects, I don't really see anything to complain about, like anything that would directly lead to bad voltage regulation. I've not yet measured the board with an oscilloscope, but I do plan to do that soon-ish. Yeah, I've got a lot of stuff to test, and there are other motherboards that I'd like to test first. So, yeah. Anyway, let's move on to the memory topology. And so in typical X670 motherboard fashion, we're looking at a, well, actually, yeah, 8-layer daisy chain, because most X670 motherboards use 8-layer PCBs, and all of them use a daisy chain memory topology. And the reason that daisy chain memory topologies are used for DDR5 pretty much universally is because with high-speed signals, you really don't want to be loading the memory controller any more than you absolutely have to, and T-topology layouts inherently put more load on the memory chips and the memory controller. So daisy chains are preferred, because with daisy chain, the only issue you have is that the timing, well, if you put your memory stick here and here, you have an unterminated, like, stub basically hanging off of the memory trace, because the memory trace goes like this, and, you know, it makes a connection to the first DIMM slot and then the second DIMM slot. And so if you put your memory stick here instead of here, you get signal reflections from this part of the trace, and that just completely screws over memory stability, which is why the board very clearly tells you to populate the outer 2 slots first, right? Like, these 2 slots are the ones that you're supposed to use if you only have 2 sticks. Anyway, where was I going with this? Yeah, so daisy chains basically are preferred because if you do have 4 memory sticks installed, the only thing the memory controller has to do is account for the timing difference between this memory stick and this memory stick, because there's a very slight difference in signal timing, which matters more and more as your signal, like, as your memory clock and, like, data rate increases. But like, the memory controller can account for slight timing differences far better than it can account for just, oh, there's more metal that I need to, you know, drive, basically, which is the issue with T-topology, which is why it's not a thing on modern motherboards anymore. Anyway, so on the top layer, we do have a just full-on, like, ground shield over the memory traces. And on the back of the board, we've got more of the same. You basically can't see any of the data queue. Yeah, so that's just how Gigabyte's been sort of doing their, like, daisy chain topologies for DDR5 boards. And here we can see the data, well, the command address bus for the 2 sub-channels of the DDR5 sticks. Because this is the command address bus for, like, this half of the memory sticks. And there's 2 command address buses that you can kind of see, like, this one's wrapping around like that to this DIMM slot. And then on the, I imagine it's on the other, like, internal layers of the board that it makes the connection over to this end. But yeah, that's just another daisy chain. In fact, I think we might be able to kind of see that. Yeah, you can just kind of see how that via connects straight to this via. So yeah, that's just a daisy chain. Anyway, so pretty standard memory topology for a X670 motherboard. And in terms of memory overclocking, I've had the board all the way up to 6400. In fact, I think I accidentally booted it at, like, 6500 when I was messing with BCLK overclocking and forgot that I had the memory clocked to 6400. So, yeah, can't really complain about that. That's kind of it, I think. Oh, wait, I guess we could mention the Vddio memory voltage regulator, which is the same as it is on the higher-end boards from Gigabyte. So you just get a Richtech RT 8120. This is the same driver plus controller that Gigabyte used on their, DDR4 boards. But this time it has to do even less work than it did on the DDR4 boards, because in the past this VRM would actually power the memory sticks and the memory controller. Now it just powers the memory controller, so it's under less load than ever before, and it's made up of 3 MOSFETs. I imagine this is one of our high sides, then we've got a low side, and if we go onto the back of the board, we get another low side over here, and these are all 4C10Ns from On Semiconductor. And these are not great MOSFETs, but for a low power application like this, they're actually just fine. And when I say just fine, I mean they're more than fine. Like they're completely, especially with a DDR5 board, because they're not even powering the memory sticks themselves, right? Like Gigabyte's been using this exact same memory VRM for years on their DDR4 boards, and now they've just copied it onto a DDR5 board, and here it just powers the memory controller. So yeah, the reason I don't consider these great MOSFETs is there's an awful lot of like motherboards and GPUs where these are used in like vCore, where, you know, you need to push potentially 100 or 100, like over 100 amps through them, and then yeah, they don't do so great. Luckily, we're not seeing that on even low-end X670 boards anymore because, well, low-end X670 boards are expensive, and also they just use a bunch of smart power stages. So that's neat. And that's basically it. I mean, I guess I could also mention the 1.8 volt regulator, but that's just the same thing that it is on the X670 Aorus Extreme. And so, yeah, that's the Gigabyte X670 Aorus Elite AX. If you're basically if you're considering X670 because you just want a lot of connectors, like 4 M.2 slots, bunch of USB ports, and, you know, then you want to like build like a rendering system with like a 7950X or something, this board can totally do that, right? Like in terms of power delivery, it'll have no problems with a 7950X. And then in terms of connectivity, that really depends on what you need, right? So yeah, but if you like USB Type A ports, this is definitely a solid option for that, because like, this is more USB Type A ports than I would be able to use. I generally, like, I need kind of a lot of Type A. But this is way more Type A than even I know what to do with. So, yeah. That's it for the video. So, thank you to Gigabyte for sending over the X670 Aorus Elite. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comments section below. And if you'd like to support what I do here with the channel, I've got a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, you know, the usual YouTuber merch. And I've also got a Bandcamp, if you enjoy, like, industrial noise. So, yeah, there's a link to that down in the description below as well. And that's it for the video, so thank you for watching, and goodbye.